Hey everyone, I'm Donovan Brown, Partner Program Manager here at Microsoft. Welcome to the open source session at Build. We are so excited that you're with us. We have so much to show you, starting with how to get the best performance from your cloud workloads while keeping them secure. Next, we'll show you how to supercharge your Kubernetes development. Then, we're going to show you how to utilize your skills in the cloud and on the edge. Finally, we'll show you how to make writing microservices easier and take your applications to new heights. So just sit back, relax, as Olivia gets us started. Here's Olivia.
Hi, I'm Olivia, and I'm a product manager too for Azure Edge and Platform. Today, I'm excited to introduce you to CBL-Mariner, Microsoft's first-party Linux distribution. The second half of this segment will be a .NET container demo. CBL-Mariner, or Mariner for short, powers a wide range of use cases, from a base and distroless container to a container-optimized host. So let's chat about how the Mariner container host is built. Mariner utilizes the Microsoft kernel, which is optimized for Azure workloads. On top of that, we add a small set of core packages needed to run container workloads. From there are 7,000 additional RPM packages available for users to customize on top of the 450 megabyte base image. Mariner is open source and available on GitHub, with a version 1 ISO that you can download and play with. Future Mariner versions will also be available on GitHub, and will include a container-optimized host. We gratefully acknowledge all the contributions made from the broader open source community, which allowed us to build Mariner. So there are many Linux distributions in use at Microsoft, so why did we create Mariner? Firstly, developing Mariner in-house has given us the opportunity to optimize for Azure. Mariner is a lightweight image, only needing essential packages required to develop and run applications in a cloud environment. With the lighter image, you get better performance and a reduced attack surface. We also run our image through a suite of Azure-specific test scenarios, helping us catch and mitigate issues before the image is released. For developers, the containers and container hosts contain same package versions, allowing for streamlined testing and a consistent experience. Mariner secures the supply chain. We build packages from source and 1ES hosted pipelines and sign each package. Like other Linux distributions, we leave customization up to the user so they can build their optimal image for their application. Lastly, Mariner offers enhanced security through secure by default principles, including a hardened kernel, secure boot, SE Linux, and confidential VM support. When looking at vulnerabilities, in some cases we've been able to achieve same-day CV turnaround. So there are a few different ways teams at Microsoft are using Mariner. Firstly, developers are using Mariner as their build platform by accessing base and distroless containers through internal pipelines. Secondly, Mariner powers various Microsoft services through its container host, both on the edge and in the cloud. AKS HCI, the on-prem Kubernetes implementation of AKS, as well as eFlow, Edge for Linux Windows, are two examples of edge scenarios using the container-optimized host. In the cloud, Office and PlayFab are two of many services using both the Mariner containers as well as the Mariner container host. So I briefly mentioned that we've built distroless containers for teams to consume, but what are distroless containers and why are they valuable? Distroless containers contain only the minimal set of packages your application needs, with anything extra like the package manager, libraries, and shell removed. Due to their limited set of packages, distroless containers have a minimized security attack surface, as well as a reduced noise from vulnerability scanners. This generally translates to a reduced overhead of patching vulnerabilities, allowing developers to focus more of their time on building their application. Lastly, the smaller size provides better performance. Mariner builds 3 distroless containers. The smallest contains only 3 packages for use, with Golang or other statically linked applications. The second container adds OpenSSL, glibc, and a few other packages for C-based applications. And then the last container adds a couple debug packages to provide a lightweight debugging environment. Next, I'm going to hand it off to Matt to talk about how he built .NET distroless containers using the Mariner base, and how those learnings are being applied to the other distributions that .NET builds on top of.
Hey everyone, my name is Matt Thalman, an engineer on the .NET team, and today I'm going to be showing you how we built .NET distroless containers for Mariner and how they're useful. Okay, the first thing I want to show is the .NET Docker file that defines our distroless support for Mariner. So this is one of several Docker files we have, but shows the most interesting aspect of dealing with distroless. And because distroless is so trimmed down, there's not even a shell to execute commands, so we have to jump through some hoops in order to be able to do the things that we need. We use a multi-stage Docker file in order to be able to install the packages that .NET depends on. So this is the first part of the multi-stage. This is the first stage here. And we're using it to install the .NET dependencies right here. And so here are the packages that we're installing. And the way that this works is that we're putting everything into a staging directory. So we're using this install root option, and the install root option maps to the change root feature of Linux if you're familiar with that. It causes the package installation to be executed in a separate virtual file system. And all the files that get written to the file system when installing the packages is all contained within that staging directory. And then down here, we're making use of the base distroless image from Mariner as the next stage within the Docker file. And here we're copying all the information, all the files from the staging directory go into the root location of that container. So that's how we're transferring all of the package files that were installed into the distroless container. We're also installing, creating a non-root user as well, right here. And so this is being done because since distroless is really meant to be more of a security constrained environment, it makes sense to be running as a non-root user by default. And by having a non-root user, you get security benefits of that. And it makes more sense to install the non-root user by default because it's not readily available to do it yourself because of the aspect of not even having a shell within the distroless container. And we also have other runtime Docker files that then use this image as the base. And they all use a multi-stage Docker file as well to simply download and extract the runtime files into the container. Okay, so now let's see what it looks like to have distroless in action with a real running app. So I've created a simple web app to show you. This is a Docker file for it. This Docker file was generated by Visual Studio. And all I had done was change the tag to be .NET 7 preview with Mariner. So let's take a look at the app. And it's just a simple note-taking app. We can see that we can add a note and it just gets displayed there. So I'm going to play the role of a hacker here and try to hack my way into this app and see what can be done. So I'm going to throw in some input here, see what happens. So there we go. We have an error right away. So I had entered in test/me, and you can see in the error that says not a directory, app/notes/test/me. So I can infer from this, it seems, that it's actually, when I enter in a note, that's actually getting stored as a file within the container. And because I had that slash in there, that got interpreted as a directory separator, and it's complaining that the test directory doesn't actually exist. And it's all done underneath the notes directory. So that's interesting. Well, I wonder if we can try to exploit that and try to maybe modify some of the application's files. So what if we did this? What if we went up a directory from the notes directory into the app directory and modified the settings.json file and see if we can do that? So let's assume I kind of know some things about how this might be configured, and it has a diagnostic mode enabled setting. And I would assume that would be set to false because this is a production app. Let's try setting it to true. Okay, there we go. Look at this. So now the app is entered into diagnostic mode up here. And now you can see up in the menu that we can have access to manage users and server settings. So I've effectively hacked into the application by modifying its settings file directly from the web page. So that's not good. What if we use distroless instead? So if I just update the tag for the base image to use the distroless one and use that as the application instead. Now, if I have a ready-made app for that, and let's try that out. So I'll just make sure that the app is still working. That all works. Now let's try that same exploit again. I'm going to try that. Okay, now we get a different error this time. It says access to the path settings.json is denied. So that's a good thing. And the reason that this happens is because we're running as a non-root user. We don't have access to be able to overwrite that file. So just by all we had to do was change the base image to be distroless, and we got this extra security enhancement within the application because we're running as a non-root user. But that's not all. Because distroless containers are so trimmed down, there's less security exposure in them, and also the image size is smaller too. So if we take a look at the original app image that I used, that was 366 megabytes, and the distroless image was only 161 megabytes. That's about half the size. That's pretty awesome. The .NET team intends to take what we've learned from implementing distroless containers for Mariner and apply it to other Linux distros as well so that the broader .NET community can take advantage of them. My name is Matt Thelman. Thank you for listening. And now I'll hand it off to George.
Thank you, Matt. From building .NET distroless containers, let's see how Azure and Azure Arc are helping you through your cloud-native journey. My name is Josh Palma, and I'm the Principal PM Lead for Azure Kubernetes Service. So let's start with some exciting new things that Azure has for you. The future is defined by accelerated innovation. Most of this innovation will be digital and will take the form of new applications. The apps of the future are cloud-native. These apps are designed to take full advantage of the latest innovation in public cloud, intelligent and infused with AI to provide advanced insights, quickly able to incorporate open source technology and libraries from across the globe. Azure provides all you need to build, deploy, and run the next cloud-native app. From managed Kubernetes, serverless containers, and serverless functions to planet-scale managed databases with high-quality vision, speech, language, and decision-making AI models. And all this integrated to the tools you love, like VS Code and GitHub. But the one thing developers love more than VS Code and GitHub is coffee. So to talk about their experience, I'd like to invite Gary, Engineering Manager, Digital Platform Engineering at Starbucks, to join me.
My name is Gary Blakely, and my pronouns are he, him, and I'm the engineering manager for the Digital Platform Engineering Foundation core team at Starbucks. We provide infrastructure and platform services for a variety of customer API, integrations, and payments teams. Those teams operate APIs and services that support portions of the experience on our mobile and web apps, as well as other integrations with partner organizations. When our team was asked to assist these teams in their move to the cloud, we immediately brought them together to identify their highest priority concerns and desires. They resoundingly asked for container hosting support that could provide high availability, high resilience, rapid scalability, multi-regionality, secure ingress, service mesh when needed, and most importantly, security requirements built in. Azure Kubernetes Service, AKS, covered all the top-level immediate needs right out of the gate and could be enhanced with services of our own to meet the rest of the stated desires down the road. Additionally, because AKS is based on Kubernetes, it provided a set of well-exercised operating and development patterns that our customer teams were eager to embrace and an expansive open-source community from which we could all benefit. With our first solution, our small but mighty team of about 8 engineers aimed to deliver a secure container hosting environment under a very tight initial timeline for our customer teams and ourselves as we all began to build for Azure. This effort was named the Collaborative Cloud Container Platform Offering, known colloquially as C3PO, a protocol droid for running containers in the Digital Platform Engineering Group. As the C3PO cluster support solution was being built, we also leveraged the flexibility of container-based development by helping our first customers initially build, secure, scan, and operate their first containers in Azure App Services, which gave them a first-mile head start as we put a finer edge on the AKS-based solution. The central precept of the C3PO offering is a distributed responsibility model under which each customer team has their own AKS cluster in their own subscription in our enterprise tenancy, running their own supporting PaaS services like Azure Service Bus, Event Hub, and Cosmos DB. Each of those customer subscriptions delegate specific permissions to the core team's tools running in our own cluster in our own subscription to act on their behalf in their clusters. Our team also provided a set of Azure DevOps templates, Terraform examples, and other tools to help support our customer team's needs for building, deploying, securing, and operating their applications in their clusters. Because Kubernetes is at the heart of AKS, we had a deep well of possibilities to draw from to find the right answers for our specific use cases. One of the key learnings from the distributed responsibility model was that most of our teams did not want to run their own Kubernetes clusters over the long haul. We also discovered some teams preferred hosting under the protective umbrella of our existing enterprise security tools, which were more readily available in our ExpressRoute connected subscriptions. Several AKS updates during the period helped facilitate the design of a new multi-tenant solution that could be connected to our enterprise network and provide robust isolation between development teams within the shared cluster. Using a combination of Kubernetes namespaces, our existing enterprise Azure AD setup, and AKS support for node pool-specific scheduling, we found a way to offer both the isolation we wanted between tenants on the shared clusters we operate, while simultaneously delivering the elegance of an independent development team ownership over the operations of their own software in production. We're doing all this with an eye towards adding services beyond compute, such as Azure Service Bus, Event Hub, and Cosmos DB on the platform in the future. I am wildly proud of our team for their tenacity and creativity in this effort. I'm also deeply appreciative of the ever-expanding capabilities of AKS that propelled us forward in this journey. The flexibility of AKS, integration with Azure, and underlying support for Kubernetes concepts, bolstered by a huge open source community, has been the engine empowering us to deliver value along the way, pursuing the immediate and future needs of our internal customers.
Thank you, Gary. If you'd like to listen more on how Starbucks uses AKS, make sure to tune in to the Customer Tech Talk session. Now, speaking of things that we love, the day Forza Horizon 5 launched, more than 1 million concurrent users put the pedal to the metal, delivering across vibrant virtual landscapes. The word spread, and within a week, 10 million unique users like me tested their driving skills. A bigger launch than any other title in Xbox Game Studio history. Forza Horizon 5 is based on Windows and the .NET framework, and now features 17 core microservices that run in Windows Server containers hosted on Azure Kubernetes Service. Shifting to the highly regulated and competitive world of financial services, Canada's largest bank, Royal Bank of Canada, have a mix of public clouds, private clouds, and on-premises resources. And we're looking to consistently deliver innovative digital experiences and continue to earn the trust of their customers. RBC application teams have been able to achieve this goal with Azure Arc-enabled data services and Arc-enabled Kubernetes, giving them access to cloud services in their own data centers, ensuring that the bank is able to operate the majority of their systems on premises because of security and regulatory requirements. The new platform shaves weeks to months of the engineering team's delivery schedules. In addition, by offloading the operational overhead to Azure, RBC anticipates saving $1 million a year in capital expenditures. Now, last week at KubeCon EU in Valencia, Spain, we announced a number of new features for AKS and Azure Arc. We announced the general availability of the Open Service Mesh extension for Arc-enabled clusters that allows Arc users to leverage a fully supported service mesh experience. For users looking for more flexibility on the networking plugins, we've announced the ability to bring your own container network interface plugin from any popular third-party and open source options. And with the general availability of Kubernetes 1.23, so did Windows host process containers make GA within the product. In addition to these, you can now encrypt the secret stored in etcd with your own key, saved in Azure Key Vault. Test Kubernetes 1.24 and let Kubernetes automatically create private link services when you leverage the custom annotation for it on your Kubernetes service manifests. As we're building AKS, we want it to be a destination for all developers and provide them with the best getting started experience on Kubernetes, whether it is their first time trying Kubernetes, launching their 100th production application, or just doing a quick test. We're excited to bring an initial set of capabilities to AKS to enable developers to start from source code and get a non-containerized application deployed to a Kubernetes cluster through Draft, the open source project that streamlines Kubernetes development. Draft will be integrated with AKS through the Azure CLI, the Azure Portal, and Visual Studio Code. It will generate everything for you, from Docker files, Kubernetes manifests, Helm charts, or customized configurations to automating a CI/CD setup for you via GitHub Actions. Integrated with Draft, we're also happy to announce web application routing, the easiest way to get your web application up and running in Kubernetes, both securely and removing the complexity of ingress controller, certificate, and DNS management, while offering knobs for enterprises looking to bring their own. Web app routing offers a managed ingress controller based on Nginx that you can use without restrictions, and it integrates out of the box with Open Service Mesh to secure intra-cluster communications. Finally, and to make our application production ready, we also want to make sure it autoscales. However, each application is unique in the parameters that you may want it to scale on. So we're thrilled to announce full integration with the Kubernetes Event-Driven Autoscaler, or KEDA, the world's best Kubernetes workload scaler that supports a variety of ways to scale your application, from Prometheus metrics to queue-based scaling with Azure Storage Queues or Azure Service Bus to over 50 different scalers. Now you can benefit from customized scaling for your workload and let AKS manage Kata for you. As you grow your digital environments, whether through Kubernetes, Arc-enabled Kubernetes, or other cloud-native solutions, the need to effectively monitor these complex environments becomes critical to delivering your business outcomes. We already offer powerful observability solutions like Azure Monitor to help you quickly detect issues and proactively resolve them, in turn, reducing outages and increasing response times. Now, Grafana is a very popular open source tool that developers already standardize on today. So with that in mind, we are happy to share we have increased our offerings in the observability space through our latest launch of Azure Managed Grafana in preview on April 18th. Azure Managed Grafana allows you to deploy your familiar Grafana dashboards without having to host your own Grafana software and fully take advantage of the built-in high availability and security from Azure. Azure Managed Grafana connects seamlessly to Azure Monitor and supports Azure Data Explorer. Using Azure Managed Grafana, you can view your Azure monitoring data in Grafana dashboards in a few simple clicks. You can also combine application and infrastructure metrics from multiple Azure sources into a single dashboard for full-stack visibility. We offer out-of-the-box Grafana dashboards to help you easily get started with full-stack Azure app and infrastructure monitoring. For example, our out-of-the-box Container Insights dashboards provide visibility into cluster and namespace utilization and node infrastructure metrics based on data stored in the relevant log analytics workspace. Azure Managed Grafana also comes with built-in Prometheus support that is a widely used open-source monitoring solution for your Kubernetes cluster. Now let's see how easy it is to use these with a demo. We will be working on the Contoso Air Flight Booking application, which is a non-containerized Node.js web application with a Cosmos DB data layer. Our end goal will be to containerize it and get it up and running on an Aks cluster securely without the scaling, and in short, in a fairly production-ready state. We'll start by cloning our fork of Contoso Air in GitHub to our local environment in VS Code, which is as easy as copying the URL as we just did, clicking Clone Repository, and pasting it on the prompt. As soon as we have our local copy, we will use Draft to containerize our application and get it ready for deployment. Running Draft is as simple as right-clicking your file explorer in VS Code, and here you can see the Draft selection menu and pick the appropriate command. In this case, we'll begin by running Draft Create. That will bootstrap our repo with the necessary files. We will pass what port our application is exposing, and it will instantly create a Docker file for us. It will then ask us how we would like to deploy our application between Kubernetes manifests, Helm, charts, and Customize. And in this example, we'll choose Helm. Now, for the application to be exposed to the outside of the cluster, we'll have to select a port for our service. And finally, after we provide a name for the application, you will be able to see in our Visual Studio Code window that all the new files have been generated. At this point, we have all the necessary files to containerize and deploy our app. And now we'll use Draft Up to connect to our GitHub repository to our Aks cluster and automatically generate the GitHub Action workflow file that will be used to deploy to our cluster every time we push changes or do a PR. By running Draft Up, we securely connect GitHub and our cluster via OIDC. So we'll provide a name for an AAD app, our resource group, and our GitHub organization. We'll then pass our Azure Container Registry, where Draft will build and push our container image based on the automatically generated Docker file we just created, as well as our Azure Kubernetes Service Cluster details. Finally, we'll select which branch from GitHub we want to deploy from and see that all our files are now generated. And Draft has completed all the necessary steps to get our application ready for deployment. Now let's kick that deployment off by committing and pushing the recent changes we've just made. And once we have pushed to our repo, we will be able to see our GitHub actions kicking off the container image build, and then deploying our newly containerized application to our Aks cluster. Once that pipeline is finished, we can go take a look at it and its results in the Azure portal. We'll go and check our services and use the IP automatically created by Aks for our application and open it up. Now, everything looks fairly good here, but there are some glaring issues with our application. We use an IP to access it, and we see that the connection is insecurely using HTTP. Finally, we don't really have any auto-scaling. So let's go and fix that with Draft, Web App Routing, and Kata. We'll go ahead and use Draft to add and configure Web App Routing to our cluster. We'll just have to pass our DNS name, which is our www.contosoair.com, and our certificate for it, stored on Azure Key Vault. You'll notice now that Draft creates a new YAML file, which is our ingress manifest, that we'll add to our Helm chart. As with any changes, we'll now commit and push them to our repo and kick off a new deployment to our cluster using our GitHub actions. As we refresh our browser, we see that the new deployment has started now much quicker. And once it's complete, we can see its outcome when we navigate to contosoair.com. We can now see that our communication to the application is securely done via HTTPS. Well, that settles most of it, but what about scaling? Once again, Draft can help us get Kata installed and configured in our cluster. Once we add it via Draft, you can see it creates an auto-scaling configuration, leverage the built-in HTTP scaler with a minimum of 2 replicas and a maximum of 30. We'll commit these changes once again and jump to our Managed Grafana dashboard to notice how some of the big traffic our flight booking app is getting is being easily handled by Kata. It will scale our baseline of 5 pods to 13 almost instantly as the HTTP requests start to spike. And you also can see any metrics and monitoring being sent by Azure Monitor for containers. So we've just seen how streamlined the experience can be to deploy an app to AKS. And the best thing is that for more advanced users, you can jump right in at any time and add your customizations and still leverage Draft as a very handy bootstrapping tool for you. Now let's shift gears a bit into operations. AKS is constantly evolving to ensure cluster operators have all the tools at their disposal to meet their and their organization's needs with ease. On the networking space, we're happy to announce the general availability of NAT gateway integration as the preferred egress option for your clusters. And on Azure CNI, we're GAing support for subnet per node pool, dynamic allocation of pods, and pod subnets, allowing you to have very granular control and efficiency for your IP space. For cluster creation and bootstrapping, we're announcing the general availability of HTTP proxy support to allow you to deploy clusters behind company proxies, and also alias miner version that allows you or your automation scripts to create clusters or node pools specifying only the Kubernetes miner version. Finally, we're announcing the preview of custom CA trust to allow you to establish trust between your AKS cluster nodes and your resources, such as private registries, proxies, or firewalls. In this case, a Kubernetes secret is used to store the certificate authorities information, and then it's passed to all nodes in the cluster. Now, AKS wants to not only be the home to all your workloads, but to provide you with the necessary features to optimize for them. With that in mind, we are super happy to announce that custom node configuration is now generally available, allowing you to customize many operating system and kubelet configurations and optimize them for your workloads. We are also releasing support for ARM-based VMs, which offer up to 50% better price to performance than comparable x86-based VMs for scale-out workloads. Now, Microsoft's latest Windows Server version 2022 brings a number of new and awesome features, many of which to boost the performance of your workloads, container environments, and Windows images. So we're absolutely thrilled to announce that AKS now supports Windows Server 2022 node pools and container images. Finally, the AKS and Azure storage teams have been working hard to deliver the best experience and performance for stateful workloads on AKS. One of the first byproducts of that work is the new version of the Azure CSI disk driver that delivers several performance optimizations and allows you to also optimize the performance of disks to match those of your workloads. We also want to make sure that we provide as much visibility and transparency as we can. So AKS will now be piloting the Aks Release Tracker, a place where you can see where the Aks releases are across the Azure regions, allowing you to see when a new fix or feature is in your region and directly map to the Aks release notes that you can see on GitHub. You can access it now in aka.ms/aks/release tracker. But now let's take a look at how we can leverage some of these great operational features to optimize one of our clusters, and how we can also extend the IP space of another existing cluster that might be running out of IPs. So let's start by creating an Aks cluster, my Aks, with Kubernetes 1.23, deployed on our new Ampere Ultra ARM-based VMs. They're these D8 PDS v5s. And we'll be using the newest Azure Disk CSI drivers, as you see here. Once the cluster is created, we are going to get its credentials and confirm that the nodes are indeed up and running, and we'll take a peek at their labels to confirm that their architecture is respectively ARM64. Similarly, if we take a look at the pods, we'll notice that our Azure Disk v2 drivers are running, and that the storage classes in this cluster are using the new provider version. In this demo, we'll use Kubestone to benchmark the performance of two disks created in the first case by an optimized storage class that our v2 drivers allow, and we'll then run a sample file system I/O workload customized to produce loads on I/O resources similar to a Postgres SQL DB. And on the second case, a disk created by a regular storage class. Now let's deploy these two workloads in persistent volumes and confirm that they are running the benchmark. Now this should take a little bit to complete. And once it's done, we can check the logs of both jobs and see how, in the unoptimized case, we have, for example, about 70K reads and writes, and on the optimized case, on the other hand, we have over 100K reads and 80K writes. But aside from better storage perf, our workload also needs some network tweaks, like, for example, configuring the max number of concurrent connections to, say, 240K. Well, in that case, we can use the custom node configuration feature to pass this setting to our new custom node pool. And once that node pool is deployed, we can confirm that it applied that configuration, alongside a few more that we did for huge pages. Now, for your Windows workloads, Windows Server 2022 has some really neat perf optimizations, as I mentioned before. And deploying it on AKS is as easy as specifying the OSQ property at node pool deployment. We can then verify that our new node image in the node pool corresponds to Windows Server 2022, and that when we get the nodes, we can see the new OS version. Now let's shift to our second scenario, where we have a cluster deployed onto a VNet, my VNet, with this 10.0008 address space. And it's using a subnet for nodes and a different one for pods, for segmentation purposes. Now, if we happen to run out of IPs, in the past we could only deploy into more subnets of the original IP space of our VNet. But now you can increase your VNet IP space even after the cluster is created. Let's go and do that. Once the cluster is created, we can add a new CIDR to the VNet, like the 172.16.00/12 CIDR. We then just need to update our cluster to pick up on the new address space, and we can go ahead to create our new subnets, first for nodes and then for pods. with the new address spaces. Finally, we proceed to create our new node pool using the new subnets. When our new CIDR node pool is deployed and we get its credentials to this new cluster, we can verify that the new nodes are in our new address space and that the old ones remain in the old address space. Similarly, the pods on those new nodes will have a new pod CIDR as well. So you just saw how to optimize your Aks cluster for your workloads and how you can extend and segment your clusters to satisfy your use cases. I truly hope you've enjoyed the Azure announcements and demos. But we do see that our customers require their environments to be hybrid and multi-cloud with workloads that span across on-premises, Azure, and other clouds. So Lior is going to show us how the Azure product portfolio is uniquely positioned to meet these diverse and evolving needs.
Thanks, George. As George shared, we are building some great capabilities in Azure to help you on your cloud-native and Kubernetes journey. Given all the application decisions you are faced with, Azure makes it easy to develop modern apps using cloud-native architectures with microservices, managed databases, DevOps support, and enterprise-grade security. Azure provides unmatched security capabilities like Microsoft Defender and policy-driven approach to governance using Azure Policy and Azure Role-Based Access Control. It also enables GitOps and at-scale management for faster CI/CD, time to market to enable agility for your end-to-end application lifecycle management. Plus, it handles all your data and AI pipeline fully managed services with the latest features and built-in capabilities like high availability and disaster recovery, so you can drive down IT overhead. With Azure Arc, we're creating bridge between all these great innovations in Azure and your existing workload and infrastructure, wherever they may be across on-premises, multi-cloud, and edge. And we're doing it in a way where you can invest in a single set of skills, processes that you can transfer wherever they're needed. Today, we're talking about Kubernetes and containerized applications. So let me share a bit more about how Azure Arc can help you here with Azure Arc-enabled Kubernetes. With Azure Arc, we offer you a lot of flexibility based on your needs by supporting a wide range of Kubernetes distributions. For customers new to Kubernetes, we provide an end-to-end Kubernetes solution with AKS on Azure Stack HCI and on Windows Server, which is easy to deploy and keep up to date. We also understand that you may have existing Kubernetes clusters. You can connect these to Azure Arc too, and ensure a single pane of glass management and security for these clusters. Whether you are using AKS or bringing your own infrastructure, developers can deploy apps and cluster configurations using a GitOps-based model. And finally, you can ensure security, compliance, and observability for all these clusters using integrated Azure services such as Microsoft Defender for Cloud, Microsoft Sentinel, and Azure Monitor. Today, I'm happy to share a couple of new updates and announcements on Azure Arc-enabled Kubernetes. First, we're excited to launch the Landing Zone Accelerator for Azure Arc-enabled Kubernetes within the Azure Cloud Adoption Framework. The Landing Zone Accelerator provides best practices, technical guidance, and automated reference implementations from Microsoft experts and engineers, so you can confidently extend cloud to your on-premises and multi-cloud and achieve business outcomes. I'm also pleased to launch Jumpstart Rbox for Devops. Rbox is a solution that provides an easy-to-deploy sandbox for all things Azure Arc. All you need is an Azure subscription. With this release, developers and DevOps engineers like yourself can quickly get hands-on with Arc and deploy your cloud-native apps and databases to any location with existing DevOps practices. Now, to show you some of these in action, let's go into a demo. Contoso Books operates bookstores across the globe. The company has been going through a major digital transformation and is updating application and infrastructure across their entire footprint, including their stores. Many of the regions they operate, especially European countries, have strict regulatory and data privacy rules, which means the customer data cannot leave the region. Contoso Books has a mix of applications. Some are internal workforce management apps that can be hosted in Azure, but it's critical to keep the customer data on premises. Contoso developers want the freedom to choose services and tools available to build these applications, while ensuring they comply with regulations. To run their apps and manage data, Contoso Books has chosen various types of Kubernetes distributions, each with its own requirements and footprint. Let's take a look at the demo I recorded and see how these services come together. As you can see, Contoso has 4 Azure Arc-enabled Kubernetes clusters using 3 different Kubernetes distributions: Cluster API, Rancher K3s, and Azure Kubernetes Service, AKS, which is provisioned on Azure Stack HCI. These clusters are running in 4 stores in 3 different countries. Let's take a look at the Cluster API deployment. As you can see, the Azure Arc agent shows important resource metadata like the backend infrastructure and the Kubernetes version. In order to take advantage of Azure Arc extensibility model, Contoso installed various cluster extensions on all these 3 clusters. These extensions will let them implement Azure services and capabilities such as Azure Policy, Microsoft Defender for Cloud, Azure Key Vault, Open Service Mesh, Githubs, and more. Looking at the Rancher K3s cluster, also onboarded to Azure Arc, we can see different metadata information and also fewer extensions, highlighting the flexibility offered with Azure Arc-enabled Kubernetes. One of the primary goals for Azure Arc is to meet customers where they are with their existing investments. Whether applications are running on a server or a VM-based infrastructure, or you already have Kubernetes clusters, Azure Arc can help manage across your environment. But what about your existing container-based applications and solutions you are using from the Kubernetes ecosystem? How do you know that your clusters are configured according to your needs? How do you know that applications and configurations haven't drifted from your desired state? How do you keep up with the ever-increasing count of clusters, locations, and cloud environments at scale? Azure Arc helps here too, with native integrations for Githubs and a dedicated Azure Arc-enabled Kubernetes extension based on Flux open source project. Using Githubs approach means Contoso developers define their apps and any config in a set of files, check those files into a Git repository, and bind that repository to 1, 10, or even hundreds of clusters. Any Kubernetes manifest or Helm chart is a fair game for Githubs. With everything in source control, everyone stays at the same page. Adding, updating, or removing configuration is reviewed and approved with an audit trail, discussion, and even test results. Let's take a closer look at some of the cluster extensions installed on the cluster. Contoso Book has defined a baseline for their Bookstore microservices application configuration and are planning to perform a blue-green deployment on all their Azure Arc-enabled Kubernetes clusters, so they can test the new version for the application front-end service. The service is designed to count how many books Contoso sold and show this information in their company internal website. Each time a book is sold, the website will capture the transaction and will update the counter. Let's take a closer look on the cluster extensions. The first extension to pay attention to is the Flux Extension, allowing for implementation of Githubs configuration, so the Bookstore application will always be up to date, based on its settings in the Contoso GitHub repository for the application. We also see that the Open Service Mesh Cluster extension, OSM, is installed as well. This will allow Contoso to control traffic routing to the application in a governed manner. These extensions are the foundation for Contoso's Azure Arc-enabled Kubernetes application deployment. Next, we will review the Githubs config and its settings. The first config to pay attention to is the config bookstore, which will initiate the deployment of the application based on the targeted GitHub repository. This repository is where the application Kubernetes manifest files are located. Let's look at the OSM config as well. This config will allow Contoso developers to test the traffic routing and web request, which will then translate to the number of sold books and split the traffic between version 1 and version 2 of the Bookstore application. This is possible since the config is also listening to the same GitHub repository, which holds the Open Service Mesh traffic routing Kubernetes manifest file we will explore here in a moment. Let's review the current application deployment. We can see that all the traffic for the number of books sold is routed to use version 1 of the Bookstore application, with no traffic going towards version 2. The GitHub repository we are seeing here is the same one we saw a moment ago in both the Flux and the OSM cluster extension settings. As you can see, the current traffic split is configured in a way that version 1 of the application to receive 100% of the web requests. Before initiating the blue-green process workflow, let's run a simple kubectl command to monitor the deployment and its Kubernetes pods. We'll come back to the repository and apply a change to the traffic split policy by updating the YAML file so 25% of the web requests will be routed to use version 2 of the application. The Azure Arc-enabled Kubernetes Githubs config that uses the open service mesh will pick up the change and will apply it instantly. So let's come back to the application web monitoring. We can now see how the change to the traffic policy resulted in 25% of the request being redirected to version 2 of the application and work as expected. By looking even closer, we can also see how Kubernetes pods are impacted by the change. Now that we have verified that version 2 is functioning and receives web traffic, let's make another traffic policy change, and this time redirect all traffic to version 2 by changing its value to 100 and version 1 to 0. Like in our previous change, the Azure Arc-enabled Kubernetes GitHub config, who listens to the repository, will pick up the change and will apply it instantly. Coming back to the web application monitoring, we can see now how version 1 stopped receiving requests and version 2 is picking up all the web traffic while the Kubernetes activity gets updated to reflect the change. As we just saw, the ability to install cluster extensions with Azure Arc-enabled Kubernetes unlock powerful options for developers and DevOps engineers, such as applying GitOps configuration and service mesh topology on any certified Kubernetes cluster.
Thank you so much. Now let's talk about writing microservices and how to take your applications to new heights. The first time you're tasked with writing microservice applications can be scary, but writing distributed applications does not have to be hard. You can let Dapr, a CNCF project, take care of all the hard work so you can focus on adding business value. You can run on-prem, in any cloud, or on the edge. No matter what industry we are in, writing software has common patterns. We reduce costs by only using the resources we need and scaling out when additional resources are required. Applications are being broken down into units of functionality, each exposed as a service. We want to focus on adding business value and not managing infrastructure. So we leverage serverless platforms and use DevOps best practices. And the number of programming languages seems to never stop growing, and we should use the best language for the task at hand. On the surface, microservice development seems simple. It's a micro or small service, not a giant, scary monolith. However, there are limited tools and runtimes to support distributed development, and many of the frameworks are tightly coupled to a language or development stack. A typical microservice might look something like this: several small purpose-built services all talking to each other. Some of the services also talk to external resources to store state or ingest events. Getting an application like this up and running and keeping it running has proven to be challenging. To address these challenges, the cloud-native community has developed Dapr, which is a set of building blocks to ease distributed application development. The goals are to take years of experience and best practices and make them easy to use from any language and on any stack. It is driven by standards and provides a consistent, portable, and open API that can be extended and used in any cloud and on the edge. Dapr is community-driven and completely vendor-neutral. At its core, Dapr is a set of building blocks, including service-to-service invocation, state management, pub-sub, bindings, and secret management, with support for the actor model and observability out of the box. You can use as much or as little as you like. If we have already solved the service-to-service invocation, but need help with state management, we can just use the state management building block. Or, if we're starting from nothing, we can use all of it, allowing us to only focus on adding business value. Any language that can send an HTTP or gRPC request can use these building blocks. Not only can applications that leverage Dapr use any language, they can run on any infrastructure. Dapr is implemented using a common sidecar pattern, where a second process runs alongside our main application. The main application uses HTTP or gRPC requests to call into the Dapr sidecar to take advantage of the desired building block. Here is an example of an application with two services, A and B. Notice each of them also has a Dapr sidecar. When service A wants to call service B, Dapr does all the arduous work of discovering where service B is and securing communication between the services. This slide also shows the pluggability of the component model. Without having to change our code, we can change where state and secrets are stored, where events are published, and even where our telemetry is sent. When developing locally, I can use a Redis container, then switch to a different backing service when we move to the cloud. The components are where the magic begins with Dapr. Switching from Redis to Cosmos DB or from RabbitMQ to Azure Service Bus requires no code changes. We just update our configuration and our code stays the same. If we do not see a component we need, they are all open source, and we can add whatever we need by submitting a pull request. To build a scalable, distributed system where we want to react to events, publish and subscribe is a very powerful way to accomplish this. Dapr supports both publishing events and subscribing to them. The application does not have to take any hard dependency on a particular implementation or SDK. We can swap out Redis in this example for any supported PubSub component. What I'd like to do now is switch to a demo so I can show you PubSub in action. First, I create a folder to hold the component definitions for Dapr. Then, I copy the default PubSub YAML to my components folder. The name of the component is PubSub. This value is needed to post and subscribe to events. The type of this component is pubsub.redis. Because this is defined in the component, it can be changed without changing any code. Next, I add a subscription.yaml file to configure where to receive events. I'm going to visit the Dapr doc site to copy the YAML needed to define this subscription. Now, I'm going to paste the sample YAML and update the information. First, I will scope my subscription to a single app with an app ID of sub. Notice the PubSub name value is PubSub to match the component I just reviewed. Next, I will set the route to where Dapr should send the events. In my web service, I will define a post method at this route. Finally, I update the topic to my topic. This will be where my events will be sent to and read from. With my component defined, I can create the apps to publish and subscribe to the events. Any language can be used that can accept a post request. I've written this application using Java and Node.js before, so today I'm going to use .NET. To publish events, I will use a console application. This will demonstrate that Dapr can be used in all types of applications, not just microservices. For the subscriber application, I will use a web API. I'm going to clean up the sample code of the subscriber. I will not need the weather forecast file, so I will delete it. I'm also going to rename the default controller file to process controller. Now, I will update the controller's name. I will remove the code from lines 14 to 17. Finally, I will replace the get method with a post. Notice that when I define the route of my post request, the name is process to match the value in my component. If the route and the route value in my component do not match, my code will not be called. In the method, I'm going to log the body provided in the request. Notice that there is no Dapr or broker specific code in the application. I simply define a post method and Dapr will make sure the events are sent to my code. Now I will update the publisher. First, I add a HTTP client to post the events to the topic. When an application is run by Dapr, an environment variable named Dapr_HTTP_port is created and populated with the port of Dapr to be used in requests. So I'm going to add a line to read that value. Now I add a for loop to post 10 events to the topic defined in the component. The body can be any valid JSON string. The address to post events is localhost on the port read from the environment variable /v1.0/publish / the name of the default pub/sub component, which is pub/sub, and / the name of the topic, which is my topic. With the code in place, I can run my applications with Dapr. I tell Dapr the app ID is sub, which is the app I scoped the subscription to, the port my application is running on, and the folder where I defined my components. Finally, I have Dapr launch my application using .NET Run. While the subscriber starts, I start the publisher with Dapr as well. Dapr starts and runs my applications. As the events are published, the logs of the subscriber are populated with the body of the requests. That demo shows just how easy it is to get started with Dapr, no matter what building block you decide to use. Earlier, I mentioned you could use Dapr on any cloud and the edge. Well, now we're going to run it on the ultimate edge, space. There are future scenarios where we may not have time to send data from space to the compute on Earth, so we must bring the compute to the data. By pre-processing raw information locally, we drastically reduce the volume of data by transmitting just the results. To demonstrate this, we partnered with Hewlett-Packard Enterprise to leverage the HPE Spaceborne Computer 2, an AI-enabled software and hardware platform aboard the International Space Station, to test a proof of concept around astronaut gloves and how NASA evaluates the condition of their gloves. Partnering with HPE, we leveraged the SBC2 to accelerate our AI NASA glove test utilizing Daprized microservices. This proof of concept employed an Azure custom vision model for glove detection and glove damage, deployed to the International Space Station via Azure Space. At a high level, the Gloves project is a Dapr-powered custom vision application. While on spacewalks, the gloves of astronauts can get worn or damaged. To test ways to cut down on the amount of time it takes to transmit data to Earth, we worked with NASA and HPE to develop a solution to bring custom AI models to the International Space Station. As NASA plans missions to the Moon and Mars, self-resiliency and autonomy becomes even more important. As the further from Earth you travel, the more important this solution becomes as data transmission becomes even more challenging. This technology tested a way for astronauts to take images of their gloves and process them on the ISS locally, providing results without requiring transfer of the data to Earth. Let's look at the architecture of this solution. First, astronauts take a picture of their gloves. Then the Gloves Monitor microservice receives the image. This service reads the image as a binary array, or if it's a video, it's read frame by frame. Next, the Gloves Monitor transmits the frame along with some metadata, tracking, and timing information using the Dapr pub/sub component. Then the Glove Analyzer microservice receives the image via Dapr. This service then runs a glove detection model to look for gloves in the picture. If no gloves are found, the image is discarded. If a glove is detected, the image is cropped to show just the glove. Next, the glove damage detection model is used to identify any damage to the glove. Then the results and timing information are logged, compressed, and written to local storage. Next, from the ISS 250 miles up, we burst down to the cloud during the next connection window. With the data in Azure, it can be reviewed using log analytics. For the AI glove test, the team was able to utilize the portions of Dapr that allowed them to focus on the problem at hand without being forced to use features they did not need. Leveraging the built-in best practices allowed the team to avoid spending time writing boilerplate code. Utilizing the pluggable components, the team was able to swap components to optimize performance with no code changes. The team members were able to develop on any platform they desired because Dapr runs the same on macOS, Windows, and Linux. The abstractions provided by Dapr allowed the code to move from the developer's machine to the International Space Station without changing a single line of code. Before I go, I would like to share a video that shows how Azure will help power our exploration of space and some additional resources. Thank you so much.
The power of the cloud is rapidly changing how organizations use artificial intelligence to monitor and validate their health and safety systems. And now, those powerful cloud development tools we use on Earth are being tested in space. Sharp corners and other hazards can damage the gloves worn by spacewalking astronauts. Currently, astronauts perform several visual checks while spacewalking, taking photos of the gloves after each walk that are then reviewed individually by a team of experts on Earth. This process depends on ground support, which will become more challenging the further away crews travel from Earth. As NASA plans missions to the Moon and Mars, autonomy onboard spacecraft becomes more important as it allows for more effective use of astronauts' time. Microsoft, NASA, and Hewlett-Packard Enterprise developed an AI workload test to run on the International Space Station that could detect damage to astronaut equipment. Using Microsoft's cloud computing platform, NASA and Microsoft created a computer vision application that identifies the condition of space gloves. Once trained in the cloud, the app was deployed to the HPE Spaceborne Computer 2, an AI-enabled software and hardware platform aboard the International Space Station, and then operated at the ultimate edge, enabling both local and remote analysis of the glove conditions. This test could pave the way toward increased autonomy onboard spacecraft, contributing to NASA's effort to test and develop new technology and techniques to support astronauts as it sets its sights on future missions to the Moon and Mars.